Hello everyone. So, welcome to the final lecture of our MIT IT IoT class. Today will be a different kind of lecture than all the previous ones. We'll be going over ad hoc problems, which are basically problems with no prerequisite knowledge, and it's more like fun and creative solutions. And for this format, we've chosen 4 problems that we think are pretty cool for you guys, and we'll give you time to think about it independently, and afterwards we'll go over the solution. So let's get right started. Okay, so our first problem is called Nezar and nice speed map. So we're given n distinct points, and we want to find a way to visit all the points such that no formed angle is obtuse. So you can see on the slide, on the left example, if we go from A to B to C, then the angle ABC is acute, and therefore it is valid. But in the second example, we're going from A prime to B prime to C prime. This angle is obtuse, so it is invalid. Okay, so for a bigger example, let's say we have these 5 points, and we start at the green one. Okay, so one valid path would be we first go to this green node and then this green node, forming an acute angle, which is good. Then we go to the top left green node, forming another acute angle, and we'll go to bottom left, forming another acute angle, and that's a valid traversal. Okay. Now for an invalid traversal, let's start at the bottom right point, and we'll go to the middle point here. But for example, we can't go to the top left point from here, because this would form an obtuse angle, and that would be invalid. Okay, so I guess that's just the problem statement. So we'll give you some time to think about a way to visit all the points such that no formed angle is obtuse. And some advice to all of you is to find a simple strategy and try not to overcomplicate it. I think in probably about 3 minutes, we'll give some hints and helpful ways to think about it. And after 5 minutes, we'll go over the solution. So I guess now would be a good time to get out your pen and paper and draw some examples and just try to solve the problem. Yeah, I'm gonna set that properly now.
What? Like ABC?
What? Is it fine right now? What's going on?
What's wrong?
It's cut off.
Oh. Do you remember what you did last time to fix it?
Wait, last time I just shared my whole screen.
Wait, just share your whole screen again.
But I have.
Just stop sharing and try again. Oh, looks good.
Interesting. Oh, you need to share full screen after we connect to the camera.
Oh, that's what makes up for the projector. Maybe the center's always
Also, for anyone just joining in, so right now we're thinking about how we would solve this problem. And if anyone has any ideas so far, feel free to just shout it out or raise your hand. Yeah.
Should I just say?
Yeah.
I'm not sure. You can take the shortest pair.
The shortest pair of points.
And you keep repeating like.
You always take the shortest pair.
No, it's the shortest.
So you go to the closest
Suppose
point.
it's AB. The shortest pair of points. Then you just keep ACB, AD. I don't know.
Wait. So at each point you go to the next the next closest point.
Draw an example on the board.
Yeah.
Or something.
Wait. So I guess how would you go. How would you solve this?
Oh, wait. Wait, no, it doesn't work. I think.
Yeah, that's okay. So I guess like one good way to solve like these problems is like you keep trying ideas and hope that one of them works. So any idea is a good idea.
This one in the Zoom challenge.
Oh.
In the Zoom chat?
Maybe we could consider the triangle so we could find the radius of the circumcircle of the triangle with the opposite angle side is not the angle. So like, could you like maybe explain like what your strategy is for like finding the next point?
Wait, that's not.
This is only like determining what it's up to.
Oh.
Yeah. So could you like is this like a strategy for finding the next point or?
Go for it once.
Okay. Okay. So one I guess one. Oh, you go backwards. One second. Okay. So I guess one helpful piece of advice is try to solve like some easier versions of the problem. For example, if your points look like this, how would you go about traversing them? And like you might have seen this before. Like, yeah, can anyone like say this strategy? Yeah.
You just like go back.
Yeah, you just go back and forth, right? And in that way, the angle is always acute. So I guess I'll maybe give like a few more minutes for people to. Oh, let's go. Yeah. Okay. So, knowing this, let's just get into the solution. Oh.
Could you at each time go to the farthest point away from like the current?
Yeah, exactly. That's exactly correct. So, our strategy will be at each point we always go to the furthest. We always go to the furthest point, and based on this example, you can see that our strategy will basically always alternate between like the two sides of our example, and by doing that, it will always form an acute angle. And in fact, let's try this on another example to just further confirm that it works. So for this example, we start at the green node, and our furthest point is this bottom right node. So let's go there. And then our next furthest point is the top left. We'll go there, and you can see we formed an acute angle. Our next point is the bottom left, which we once again formed an acute angle. And for the top right point, we also form an acute angle. So after working through some examples with your strategy and seeing it work for all of them, you might want to just code it up and submit it, or you can also prove it. So for this proof, we'll be using a proof by contradiction, as most proofs are. So let's assume that we followed our strategy but ended up with an obtuse angle. So to contradict ourselves, we want to show that if we found an obtuse angle, then clearly we have not followed our strategy. So in this case here, let's say we went from 1 to 2 to 3 and then to 4. And this is an invalid path. But now we'll show that if this was the case, then we didn't follow our strategy. And can anyone identify like why this does not follow our strategy?
Because 3 is farther than 1 than 2.
Yeah, exactly. So if this was the case, then we would have gone directly from 1 to 3 instead of 1 to 2. In other words, in an obtuse triangle, the longest side is opposite to the obtuse angle. Yeah. Okay, so that's the first problem. I guess we'll move into the next one now, which is an interactive problem. So for these types of problems, you're not given all the information, and instead you need to ask queries to an interactor to gain information and determine something. So for this problem, there exists a hidden string S consisting of zeros and ones, and in one query you can ask how many times does my string T appear in S, and within 3 queries you want to identify at least one character in the string. And what that means is that I want to basically say I know that at index I in the string S, its value is either a 0 or a 1, like to determine which one it is. And so let's go into an example here. Let's say n equals 4, or our hidden string has length 4, and we query the string 1001, and we're told that 1001 appears exactly once as a substring of the hidden string. Now, can anyone tell me what are the possible strings that could be hidden? Yeah.
Like 1001.
Yeah. So it's basically just all the combinations that contain 1001, right? And let's keep asking queries to narrow down these possible strings even further. Let's say I ask 010, and I'm told that 010 occurs no times. Then what do? So I see that for these two strings, 010 occurs once. So therefore, these two strings cannot be my hidden string, and I can just remove them. Okay? And final query, let's try to figure out which one of these two strings it is. I'll ask 110, and I'm told that 110 appears exactly once in the string, and therefore it can't be 10011. It can't be this one. And so I'm left with my final string. So in this example, we use our 3 queries to determine exactly what the hidden string is. But in our problem, our task is actually a lot easier. We only have to identify a single character of the string. So here I've highlighted at each point which characters we can identify. So in fact, after the first query, we already know that the middle character is always a 0. So we could immediately terminate and output that the middle character is a 0. And if we keep asking queries, we have more information. Like after the second query, we know the first character is a 1, middle character is a 0, and the last character is a 1. And after the third query, we know the entire string. Okay, so now let's try actually interacting. So instead of just thinking time, I have come up with a string of length 6, and I'll let you guys try to determine 3 queries to ask to figure it out. So if you have any ideas, feel free to raise your hand, and we can undergo an interaction. But otherwise, I'll give you time to come up with a strategy. Okay.
Wait, I have a question. If a string is 1111 and you query 111, is it going to return once?
Okay, so if the string is 1111 and you query 11,
Yeah, sure.
so if you query 11, then it'll return 3. So basically, the overlaps are counted.
Okay.
Yeah. Oh, wait, it's been chat messages.
I answered some of it.
Oh, okay. if anyone wants, they can also try with a string of length to figure out a string of length 3.
Yeah, we could start. I guess I want to just say a random.
Oh yeah.
That could be in the string.
Okay, so anyone want to just give any query at all to just start off?
101.
101. Okay. Okay.
Can you remember the whole
So 101 occurs 2 times. So let's record this down. My string has length 6. And 101 occurs twice. Okay, I guess this narrows it down a bit. So anyone want to try to give it another guess? Good.
10101.
10101. Okay, so now I will say that 10101 occurs once. Other good guess. Okay.
0 1 0 1 0
0 1 0. And 010101 does not occur in the string. Okay, so now can anyone figure out any character of the string?
The first character is 1.
Yeah, so the first character must be 1, right? Exactly, and the string was 101. Yeah, so these are actually some very good queries. Narrowed down the solution by a lot. Yeah, okay. So that's like kind of a sense of what kind of queries we're trying to ask here. So I guess let's just get into the solution right now. So if we look at our problem, we're trying to find both an index and a value. And I guess for this one, you guys have figured out that instead of choosing any index, because there's a lot of indices to choose from, it's better to just target the first one or the last one, because those are like kind of special, right? So in this case, you guys managed to guess the first character. But in our solution, let's say we're trying to guess the last character. Now that we know what our index is going to be, let's figure out the cases for what happens in each of the value cases. So what if the last index is a 1? Well, the main and pretty clever observation for this problem is that every single 1 in the string will be followed by either a 0 or a 1, except for the last index. So here you can see that the first 1 is followed by a 0, the second 1 is followed by a 1, the third 1 by another 1, the fourth 1 by a 0, and the fifth 1 by a 1. Except the last index, if it's a 1, is not followed by a 0 or a 1. And you can do that here. Now, how does this help? Well, actually, can anyone see how this would help right now?
You can like query 1 0 and 1 1 to figure out like how many 1s there should be. Like, kind of.
Yeah, exactly. Right? So if we query 1 0 and 1 1, then we know how many 1s there are that isn't not including the final 1, right? So that motivates us to query the number of 1s, the number of 1 zeros, and the number of 1 1s. So if the last index is a 1, then the number of 1s will not be equal to the number of 1 zeros plus the number of 1 1s. And an example here. So our last index is a 1, and there's 4 1s in the string, but the number of 1 zeros is 2, and the number of 1 1s is 1, and these don't add up. Now let's look at the other case. If the last index is a 0, then they're equal. Going to this example, the number of 1s is 3, the number of 1 zeros is 2, you can see these two, and the number of 1 1s is 1. and these are equal. So that actually just solves the problem. So our three queries will be 1, 1, 0, and 1, 1. And by using these numbers, we can determine if the last index is a 0 or a 1. And I guess some more helpful way that you could have got here is that you know that you're only given 3 queries, which is a very small amount considering the string can be of size 50. So you know that your query string length should probably be small because you only have 3 queries. And if you query a big string, you can't really get that much information out of it. Okay, so third problem. Basically, in this problem, you're on a circle with n sectors, where n is an unknown number of at most 10 to the 6th. And these sectors are not necessarily ordered. So you initially start at sector x, and you can query to move clockwise by k sectors. And you will only know your current sector before and after a query. Your goal is to figure out the size of the circle, or n, within 2023 queries. So an example of this would be, let's say I start at 1. So I'm told that I'm at sector 1, and I move 3 sectors clockwise. And now I know that I'm at sector 6, and note that the difference between 6 and 1 is 5, but I've only moved 3, and that's because the sectors are not necessarily ordered. So like they could be ordered like 1, 3, 4, 6 or something. Not 1, 2, 3, 4. Yeah. So for my next query, I'll move 4 sectors clockwise, and let's say I end up in sector 4. And next, I'll move 3 sectors clockwise, and I end up back in sector 1. So can anyone figure out what the length of what n is based on these 3 queries? Yeah. 9. It's close. Wait. Yes. Okay. So why do we know that it's 10? Because we moved 3 this way, we moved 4 this way, and we moved 3 to get back. So that's 10, probably.
Oh wait.
Wait a second.
Three plus 4 plus 3 is 10.
Yeah.
Yeah.
Okay. So in that example, completing the loop, we knew that we completed the loop in 10 sectors. So n was 10 in that case, but that's not always the case. For example, let's say I start at sector 1, I move 1 sector clockwise, and I end up in sector 3, and then I proceed to move 9 sectors clockwise. But now I'm confused. And after moving 9 sectors, I end up back in sector 1. But now I'm confused because I don't know how many times I've gone around the circle. So can anyone tell me what possible values of n there could be that would result in the same outcome here?
Like 2, 5, or 10.
Yeah, that's correct. 2, 5, or 10. Actually, 2 is technically not possible because we see 3.
Wait, that's not true.
Wait,
It's still possible.
no,
The
3.
number,
The number 3 is
not
not the
like
circle.
1 to n.
Yeah.
Oh, I
Yeah,
see.
yeah.
No way.
Yeah. So, but if we didn't see 3 here, it could be 2, 5, or 10.
So in the previous example, why was it not 2 or 5?
Well, okay. For what? For one, the numbers are 1, 4, 6, but also, like. You know that in your third move, you move 3 sectors clockwise, which means that if you looped around, then like you wouldn't like loop back around. It's like
It could still be 5. If the 6 didn't exist, it could still be 5.
Wait, yeah.
Yeah.
3. Yeah, the 6. If the 6 didn't exist, it could be 5. No?
Yeah.
Okay.
Okay. Okay, so I guess we'll give everyone some time to think here. Just think of like a strategy that you could use to figure out n. Okay. Yeah, and if anyone wants, we can run the interactive with n equals 12. And
Oh no, you still.
okay, wait. We'll run it again with some random hidden n. And although you are allowed to use 2,000 queries, please do not use all of them.
This is probably better.
Okay. Yeah, so let's just say you start off in sector 1. And does anyone want to like start off by giving an amount you want to move? 1. Okay. Let's say you ended up in sector 11. 2. Okay, let's say you ended up in sector 3. Sorry? 8? Okay. Let's say this puts you in sector like 21. I'm realizing that this will not form a circle.
That's fine. Wait, just
No.
like draw as a line.
Yeah.
Draw as a
Yeah.
line.
I don't know. Okay. Well, let's say this is our current like information. Yes. Yeah. Get 21. Okay. I don't want to give another grade. 10. Let's say you ended up at 9.
Just keep the numbers as small. They don't give any information.
Okay. Any more numbers? 2. Keep it small. Say you end up at 2.
$100.
Okay, one second.
Oh.
Yeah, 3.
Okay, yeah. Okay, well now you have a lot more information. Actually, is it possible to determine n from this information so far?
Shouldn't be.
Not yet.
Not yet.
41 or 1.3?
Huh?
Wait, or wait, no, I'm not.
Okay, so any more numbers?
60.
60. Okay. So back at 3.
30.
30. You end up back at 3. Can anyone guess what n is now?
Yeah.
Yeah.
30.
30. Yeah, it's 30.
21 was a blunder.
Okay, so from this example, like you might have realized that you basically have like no information until you run it into a number you've encountered before, because they're randomly computed, right? So I guess this motivates our strategy, being to first gather as much information as possible. That is to say, we should like make it much a small walk to gather up some information. So let's go back to some more motivation. So why do our big queries fail? So when Ballin queried his 100 here, we ran back into 3, but we didn't know how many times we looped around. And we showed this in a previous example as well. For every big query where n is the query is bigger than n, we could have many values of n to choose from. Okay. Now, why do our small queries fail? Why can't we just walk all the way around the circle? Well, we just don't have enough queries to do that. Like if I just walk 1 every time, I can't walk a million times without exceeding my query limit. Yeah. So in this example here, we just keep walking and we never figure out what n is. So what if we combine the two? And let's also bring this back to like information. So in our first step, we want to use our small queries to gather as much information as possible. So let's say we move forward by one sector 1,000 times. And here I've shown this in green. And without loss of generality, we can assume that n is greater than 1,000 because otherwise we would have looped back around and we would already be able to determine what n is. So now we have like a big patch of information that we know. Now, how can we use this? Now, let's move forward by 1,000 sectors.
Oh wait, I thought you were like asking. Yeah.
Oh, okay. You wanna?
Move around. You can like query 1,000 times.
Yeah. Yeah. So you do that, right? And I'm pretty sure you would have figured that out without me going to the next slide. So yeah, pretty cool. So now let's move us forward 1,000 until we loop back across one. And here we're taking steps of 1,000. And can anybody like say why we know that eventually we're gonna end up in a green square? And once we do end up in that green sector, how can we determine n from it?
N is the most data 6.
Yeah.
So like you will look at this once.
Yeah. So.
I guess the question is like, how do you know you're ever going to land on a green square? What if you skip the green patch?
No, you don't know, but once you look at this once.
Like no, like how do you know that you're going, like you're eventually going to land on it? How do you know you're not going to like skip it?
Because I was like 1,000.
Exactly.
Yeah.
So anyways, as you said, n is at most 1,000,000. So if we keep walking forward by 1,000, in 1,000 queries, we're guaranteed to always loop across it. And as he said, when we loop across one again, we're gonna always end up in a green sector because there's 1,000 green sectors and they're all consecutive. Now, using this information, we're able to determine n. Why?
You can go one by one.
Yeah. So I guess you know how many you know how many big steps you took, and you know which green sector you ended up in. And using that, you can just do some calculations and solve for n. Okay. So this is actually a concept called baby step, giant step, which there is a link to here if you want to learn more. And it's useful in number theory and stuff. Okay, so our final problem, tricky multisets. Basically, you're given a multiset of size n, where the element I appears a of I times, and note that I goes from negative multiset is n. Multiset with 2n elements, where the elements negative n to n each appear a of I times. And in one operation, you can basically remove two elements x and y such that the difference is 2, and you insert their average twice into the multiset. And I guess this makes much more sense with an example, which is here. So here, I have two negative 3s, one negative 2, 1 0, two 1s, 1 2, and 1 4. And let's say I want to do the operation on my 2 and 4. So then I erase both of these from the multiset, and I add in two 3s, which is their average. And remember that I can only do this operation on 2 and 4 because their difference is 2. Okay? Now, our goal is to make every element in the multiset 0. So let's just see how we could do that in this case. So let's take our elements 1 and 3 and merge them into two 2s. Let's take negative 2 and 0 and merge them into two negative 1s. Let's take negative 1 and 1 and merge them into two 0s. And let's take negative 3 and negative 1 and merge them into two negative 2s. And let's just like speed up the remaining actions until we finally reach a state where every element is 0 by doing those operations. So I guess now I'll give everyone like maybe 5 minutes to think about the problem, and maybe like 3 minutes in we can like give some nudges towards the right thought process.
The question is how many operations?
Yeah.
Oh.
What was it?
The slides. There, what number slide is this?
Also, make sure you hide this. I think it interferes with your.
Oh. Fix all the errors.
No, it's just.
Alright, good.
Huh? Am I not editing the right slide?
You're on an earlier.
Yeah, you're on the earlier one.
Oh, whatever. This one is also wrong. What do you mean in total? That doesn't make any sense.
So what's the minimum number of operations to get everything to 0?
Yes.
Oh.
Spoilers.
That's the problem statement.
Oh.
What if all the elements are equal?
Oh, it's guaranteed that it's always possible.
It's guaranteed that it's always possible.
Minimum.
Wait, what if you just copy the original problem statement?
Okay, there you go.
Wait, can you refresh the slide again?
Okay.
I think it's so the answer is going to I think it's like the sum of the squares of all the elements divided by 2.
Yeah, wait, that's exactly correct. Good observation. So I guess like we'll just get into the solution then. How do we get to that like seemingly random like number? So let's first introduce the idea of invariance. So in like problems with lots of operations like these, they can like get quite messy. Like there's like operations have like you have to maintain like the order, the whatever, everything. You have to like maintain the whole multi-set if you want to do operations on it. So instead, what if we could represent a multi-set using a single quantity instead, which is let's say it's an invariant. So a quantity that never changes over time. So for an example, the sum of elements in our multi-set is an invariant, which is always 0. Otherwise, it's not possible to make all elements 0. So example here, -2, -1, 0, 1, 2. So initially the sum is 0. After we perform the operation on 0 and 2, you get 2 1s. And after you perform it on -1 and 1, you get 2 zeros. And after all these operations, the sum is still 0. And you can easily show this by seeing that x plus y is equal to 2 times x plus y over 2, which is basically you're removing x and y from the set, and you're inserting 2 of x plus y over 2. And so these will just cancel each other out and not change the sum. Okay, so what are some other statistics of the problem that we can look at? What about the sum of x squared, or the variance of the the multi-set, if you do statistics? Well, let's look at this case. The sum of x squared here is 44. Just trust me on that. If I do the operation on 2 and 4, and I merge them into 2 3s, then my sum of x squared has become 42. And you can see this is true because 2 squared plus 4 squared is 20, and 3 squared times 2 is 18. Okay, and let's just keep doing this. Oh, it decreased by 2 again. Like you can see that after every operation, the sum of x squared goes down by 2. And until eventually, when all elements of 0 are 0, the sum of x squared becomes 0. And here's like kind of the math behind why that is true. I trust that you can work through it if you want to. Yeah. So now we've noticed that the sum of x squared decreases by exactly 2 for every operation, and when all elements are 0, the sum of x squared are 0. So therefore, the number of operations must be the sum of x squared over 2.
Alright, thanks Thomas. That was the end of this ad hoc lecture.